In the past 4 videos, our focus has been on quantizing the radiant energy of electromagnetic waves, including light. We have seen how previously used statistical methods led to the so-called ultraviolet catastrophe, which was solved using the quantization principle. The photoelectric effect and the emission of electrons from metal surfaces were also explained using quantization. Finally, we saw how Compton's experiment on the scattering of energy quanta actually established the particle idea of these quanta, which became known as photons. In this video, we'll follow the post-Compton timeline. In 1924, Louis de Broglie presented in his doctoral thesis in Paris, based on special relativity considerations, and in light of the recent developments in physics of that time, a new theoretical idea. His hypothesis, which I prefer to describe as the huge step forward, ultimately laid the foundation for our modern understanding of quantum mechanics.
De Broglie carefully considered the wave-particle problem for the light quanta. He wanted to create a theoretical model that more consistently unifies both the ideas of wave and particle. De Broglie proposed a periodic phenomenon associated with material particles, such as the electron. This periodic phenomenon has its own frequency. Like all phenomena in nature, this one too can also be observed from any inertial frame of reference. According to Einstein's special relativity, the rate of time progress changes in inertial references that move relative to each other. The faster the movement speed of a reference, the greater the effect of relative time lag or time dilation in that reference relative to slower references. We'll consider 2 frames of reference, the particle frame and the outer observer frame. In the frame of the particle, the periodic phenomenon is a purely temporal phenomenon. In other words, an observer moving with the particle will measure the time period of the phenomenon and will obtain the frequency f. We can plot this through a space-time diagram. The y-axis represents time and the x-axis represents one of the spatial coordinate axes. Note that the evolution of the periodic phenomenon is purely temporal.
Now we will switch to the inertial reference of an outer, stationary observer, with the particle moving in front of him with speed v. This observer, as we said, will measure a frequency lower than f, the one measured in the particle's frame. If we follow the Lorentz transformation from the particle's frame of reference to the outer one, we can see that here a forced spatial extension appears in the observer's frame, the primed frame. We can see this because the line of dots is skewed in this frame, and the dots themselves oscillate at different times. Consequently, the periodic phenomenon has become not only periodic in time, but also periodic in space. Hence, the idea of the wave began to enter the world of point particles.
We will now derive the de Broglie relation and see how what is known as the de Broglie wavelength is a product of special relativity and Lorentz transformations in space-time. At some instance, t, say t equals 0, in the particle's reference, one single oscillation period in the observer's frame is. With Lorentz transformation for time, and with t equals 0, we have. Let's now solve for x. So for the same period, x is. To find that spatially extended new wavy phenomenon, we use the spatial Lorentz transform with t equals 0, and we get. The relationship between energy and frequency is. Therefore, the frequency will be. If we substitute this into the x prime equation, we find. Or in terms of the wavelength corresponding to one period. This is the de Broglie relation. This wavelength is infinite in the particle's frame of reference because the points are in phase. In the outer observer's frame of reference, the Lorentz transformations actually dephase the points, and this generates, as de Broglie called it, a phase wave.
This is the origin of wave-particle duality for matter in quantum mechanics. We also notice that for slow particles, the Lorentz gamma factor in the denominator is approximately 1. Therefore, this wave-particle duality also holds for slow particles. In 1928, Clinton Davison and Lester Germer presented the results of an experiment involving firing electrons onto the surface of a nickel crystal. They noticed that electrons are subjected to diffraction. At an energy of 54 electron volts, the diffraction was at an angle of 50 degrees. Using Bragg's condition, they found that the wavelength that gives this amount of diffraction should be. And since the energy of the electrons is known, their speed can be found and substituted into the de Broglie relation. When Davison and Germer did this, they found that for this energy, the corresponding de Broglie's wavelength is equal to. Notice the remarkable agreement between Bragg's law, typically applied to waves, and de Broglie's theory formulated for particles, and with this, the wave property of particles was confirmed. Thanks for watching.